Hey everyone. As you can see, the topic is very wide, so it is a bit hard to finalize every use case about these Go channels. So let's start within a couple of minutes. And this session, basically, we'll have a look at how can we handle this rate limiting stuff by using Go routines, and some kind of tricks. In last session, we just check how we can implement a ticker. Basically, we verified it by using time package. And now we will try to implement rate limiting finally. So before jumping into actual implementation, let's have a look at a couple of terms. The following shows such an example borrowed from the official Go wiki. Do you know what is rate limiting? First, maybe we can have a look. Rate limiting, let's check the wiki. So let's say that you have a service, and most probably this is a typical software as a service product, and it can be a API, it can be a public API or a private API, and you may want to put some kind of limits on these endpoints because there can be several reasons. For example, about performance, about plan. For example, you just subscribe to a service, and let's say that you have a what can it be, the throughput limit, or you have some kind of request count limit. For this kind of situation, you basically implement a rate limiter there, so that based on your plan, the customer may have different set of behavior from the service. Or maybe you just wanted to deny some kind of resource exhausting. I am a customer, and if I am able to send as much as request to that specific public API, then it may be a bad scenario for the API owner, right? So somehow we need to define what will be the possible request limit within this endpoint. When you check GitHub API, for example, you cannot just send request infinitely to this endpoint. They have a limit on this. And whenever you send a request, you get a response, right? Inside the response headers, you see how much request remaining after this specific request. So maybe I can show you this GitHub GitHub rate limit. Okay, when using GitHub, let me zoom this a bit. When using the building GitHub token in GitHub Actions, the rate limit is 1000 requests per hour per repository. So this is a typical limit on GitHub side. It says that whenever you use GitHub Action, there is a built-in GitHub token. You can just use it in your jobs. And here you will have 1000 request limits per hour, within hour. For example, you are checking if the current request is a pull request or a push or a pull, some kind of, you are checking events, or maybe you are checking what are my repositories, etc. Whenever you do these operations inside GitHub Action, you will decrement your limit within these requests for the per hour interval. Let's have a look at official implementation and official description in the wiki side. In computer networks, rate limiting is used to control the rate of the requests sent or received by a network interface controller. So this time it emphasizes the control the rate of the requests. So you are sending a request to the system, and there is a rate for this, right? For example, 10 per minute or 100 per second or something like that. It can be used to prevent DDoS attacks, as we already mentioned about this, to deny resource exhausting and limit web scraping. Yeah, this is also another stuff. Let's say that you have a e-commerce application, or you have a book application. You have lots of products, SKUs in your e-commerce application. And let's say that there is a hacker that's just clone your website. I mean, just get the SKUs from your website and just construct another e-commerce out of it. So if you put this kind of rate limiting, you can just deny this kind of web scraping, right? So what is this web scraping? Basically, I go to your category, I mean the category of your website, and then I am visiting all the possible links there. So if you put a rate limiting there, then you can just deny this web scraping. Okay, it is something like the prevention mechanism for different kind of attacks, or I mean, it may be related to your business use case, like plans, subscription, this kind of things. One of above section has shown how to use trisend to do peak limiting. We can also use trisend to do rate limiting with the help of a ticker. In practice, rate limit is often to avoid quota exceeding and resource exhaustion. The following shows such an example borrowed from the official Go wiki. In this example, the number of handled requests in any 1 minute duration will not exceed 200. You see, the interval is 1 minute, and within 1 minute you cannot do anything more than 200. This is your limit. Okay, maybe we can create another package. New directory, rate limit, and inside rate limit, go file, rate limit. So there is a request interface, request, and then there's an interface called, there is a function which is handle func handler, and this takes a request, and then the main idea within this function is fmt.println r.int. Okay, this is a casting operation, so this is a request, and when you say r.int, this will be casted to an integer. This is how we cast in Golang. Okay, const rate limit period. So the rate limit period is time.minute, and another const is rate limit 200. Okay, basically most probably we will do 200 something in a minute. Okay, there is another function which is handle requests here. Okay, then another channel requests. This time this is a receive only channel request. Inside this function we just define a quota, make, this is another channel, time, and rate limit. You see, this rate limit count is just past this one to this buffer channel. So you can put to this channel, you can put only 200 items at the same time here. Okay, just independent Go routine here, and inside Go routine there is a tick, time dot new ticker. Okay, cool, rate limit period divided by rate limit. Is that correct? Yes. And remember defer is used for so this defer will be executed at before exiting this function. So you guarantee that this tick.stop will be executed just before exiting this function. That is the main idea. Okay, let's move forward. For t is equal to range tick.c. Basically, we try to select something, case quotas t, and there's the default. Okay, so what it does here, what it does, this is a go routine. We define a channel here, and this channel is used here. In this channel, requests, where are your requests? Okay, in this channel, we are trying to put a value. You see that this t is sent to this channel, quotas channel, and there is no direction definition within this channel. We are trying to send values to here in the case. Let's see another function here. After this go routine, there is another range function. Let's see what it does. Range requests. Okay, here it just tries something from quotas channel. Here we send to tick. So remember this tick.c, it is ticking. Whenever it ticks, it's just a tick value to quotas channel. Whenever you send a tick to this quotas, it will be consumed here. Basically, we do not send, we are not interested the value of this one. That's fair enough. With this R, we are handle or handler. Should it be handler or handle? Handle. This should be handle, and this will be R. So let's say that you are just processing the request. Here it is just prints this value to the standard output. Whenever there is a request, then we just read the value from the quotas channel, but there is a logic here, handle requests. There should be some usage here, and func run here requests make chan request go handle requests for I is equal to 0. So this is an infinite loop. Within infinite loop, we are trying to send value to this channel as I. Come on. Okay. When you say run, there will be an infinite loop. Within this infinite loop, we are sending the index value 0, 1, 2, 3 to request channel. This is a channel. So and you see it is handle request function. Let's have a look at this one. Within this channel, we are trying to handle something here, right? Tick time new ticker here, and default tick stop. So we are trying to send this tick value here, but most probably it is done on this part. Maybe we can check this ticker here, rate limiter period rate limit. Let's check parameter of this, the duration. the duration d must be greater than 0. So that's why we are trying to do this one. Okay. So the keyword here is this one. The duration d must be greater than 0. Period slash rate limit period time minute, and this one greater than. Okay. Okay, let me run this one. Rate limit. So when we divide minute by 200, so 260 seconds, if you divide 60 seconds per 200, it will be something like 3 requests in seconds, right? So we are getting 3 requests, 3 numbers here per second. For every second we are getting 3 requests basically. So that is very normal, right? Whenever, okay, think about something like this. You provide a minute here, you provide rate limiting. So let us adjust it, right? I'm changing this value. Okay, so this is 60 seconds. There is a value which is that means every second we will handle a request. Let me try to, you see, every second, and when I do this, just changing to 30, that means every 2 seconds you can do something. Let me check it. 1 2 1 2 1 2 1 2 1 2. Yeah, that's it. So this rate limiting is performed by using ticker. That is the main idea. If you pass your frequency, which means the duration in your ticker, if you say your duration to your ticket, so if you provide 30 minutes and the rate limit period is minute, divide this one, minute divided by 30, then you will get 2 seconds, right? Your duration will be 2 seconds. That means for every second, think about this, for every second there will be ticking operation. For every 2 seconds you are sending a value to this quotas channel, right? Whenever you send a quota channel here, you see you are basically calling the handle function and it prints the value to the standard output. Simple. Let me close this one. Of course, in your production use cases you don't need to implement this one on your own. You can just use another library to do that, especially if you are using some kind of REST API frameworks. There is a built-in or some kind of utility package for rate limiting. Switches. From the article Channels in Go, we have learned that sending a value to or receiving a value from a nil channel are both blocking operation. Okay, if you try to send something to nil channel, you will be blocked. If you try to read something from a nil channel, you will be blocked. By making use of this fact, we can change the involved channels in the case operation of a select code block to affect the branch selection in the select command. Think about this branch selection. It is something like switch case. So in selection operation, case value. The following is another implemented by using the select mechanism. In this example, one of the 2 channels variables involved in the select block is nil. The case branch corresponding to the nil channel will not get selected for sure. We can think such case branches are in off status. At the end of each loop step, the on-off statuses of the 2 case branches are switched. Let's analyze this one. Okay, so inside the main function there is a table. Table means make. We are trying to make a channel, type of bold. Here, think about bold. It is a unsigned integer 8. Go play a table false. So here play function, the player name, player A plays something on the table, the value is false. Play B. Okay, this is concurrent, the executing, and this is a normal imperative execution. Okay, let's see the function. Player name, table, and serve. Var receive send chan bold. Here there is 2 channels, receive, send, and both has type channel including bold values inside it. If serve receive send is equal to nil, table. So receive nil, send table. In the else statement we have vice versa. Okay, var last value bool is 1, select. Here we are trying to get read from last value channel and passing it to send. So think about the first case. Last value bool is equal to 1. Okay, no, sorry for that. Last value is just a value. We are trying to send this value to send channel. Think about send channel here. They are both bool. There is no limit. It is not a buffer channel. There is no direction inside it. And we are sending last value to send channel. Okay, which there is another case. Value is read, being read from the receive channel. So we send this one to send channel. Is there anything inside receive channel? No, this should be blocked, right? There is a receive channel here, receive, but basically we do not get any value from it because there is nothing there. Player name value is equal to last value. So on every operation we are changing these pairs. Receive send is equal to send receive times second. Okay, we already have a ping pong here, and I can just copy this one and say that ping pong switch this one, ping pong shift F6, ping pong switch. This time it will be 8, but the function is a bit different. Table make chain bool. There is no go func here. Go play a table. Okay, this is for switch operation, and this will be true, and here add bool factor. This will be serve. No, change a world. If serve receive send is equal to nil table, otherwise it will be receive send is equal to table nil. Okay, then the last value bool is equal to 1. We do a for. Okay, there is no table there. We need to use select here. Okay, I will delete this part and say that select case send for this case there is nothing. Value is equal to layer name value. there should be a switch. So in most of the languages, in order to do this one, you need to use a temporary variable, right? Just use the temp variable to replace. There is also this notation in Python language, so here it is the same. Let's revisit it one more time. Player name, try to send a ball to a table channel. So table is a channel. If you at first this serve is false, serve is false. Since this is false, it will goes here, right? Player sends something, so that's why receive here receive. So table receives something, player sends something, and table receive it, and send becomes nil. Last value is 1. Let me check. Last value is 1. Okay, so think about this for loop. Last value 1 is sent to send channel here, but send channel is table, so this is a table channel, so last value is sent to table channel. What about value? We are trying to receive something from it. Receive means here okay, since serve is false, it will go to this condition, right? Send is false, that means send channel is nil, receive channel is some channel. When you try to send last value to send channel, most probably it will be blocked, right? Since this is blocked, is there any default? No, it will go to here. So since this is blocked, it will go to the second case on here. So in this part, we are trying to receive something from receive channel. Receive channel, what is it? It is just a table, right? This is table. You are trying to get something from table, but actually there is no value inside it. So who puts this value? This one. So this part, B, player B, sends something on the channel, but the serve is true. You hear and receive nil, send table. So receive. But on this case, since send is a table, the last value will be sent to send channel, which is 1, and we will be able to get it. Okay, the logic seems a bit complicated, but when you try to write down this one by one, it becomes meaningful actually. So here you see there's a switch operation. If it is serve, it is doing something. For example, if it is serve, if it is true, if you are trying to serve something, that means you need to be ready for the chance, but the receive is nil. Serve, let's say that you are hitting the ball. When you say hit the ball, then that's why the send channel is tabled. We just copied this one, but what about package? Yeah, package is not changed. Switch. On the previous ping pong example, it was just something like the Fibonacci series. You see the previous n-1 and n-2, the summation of n-1 and n-2 is equal to n. So here 3 is equal to 3 plus 1. 5 is equal to 3 plus 2. Fibonacci. Okay, the following is another non-concurrent example which is much simpler and also demos the switch effect. This example will print 1 2 1 2 when running. It has not much usefulness in practice. It is shown here just for learning purpose. Let's see. For loop. Within the for loop we define a channel type of struct, and it is a buffer channel which has a capacity 1, true. So you define something and saying true. So most probably this is an infinite loop. Select inside the case. So we are trying to send a struct to C channel, right? Is that true? Yes. Initially you can send to this one. You can read from it. You can send and you can read. Correct. 1 second delay. Okay. Yeah, basically you are sending a value to channel struct and you fill the capacity and then you read from it. It seems simple. Control code execution possibly waits. We can duplicate case branch in a select code block to increase the execution possibility weight of the corresponding code. Okay, the main function here, we initialize two channels with a type struct foo bar. We close channel foo close bar for demo purpose. We are trying to close both of the channels. There is some double values here, x and y. F is equal to func. Okay. For 100,000 times we are trying to select something. Let's see what happens. If you can get something from foo channel, the f function will be executed. If you try to get something from foo channel, the f function will be executed. If you try to get something from bar channel, the g will be executed, and the possibility of the f function, double of the okay. Okay, I just want to execute this function here. Let's make this main 1 and run this. Okay, instead of calling this, I just replace them from here. I'm not interested with this. No. So, one break miss. So I couldn't get it. One break miss. What do you mean by that? Do you mean this one? No? Yeah, deadlock, because the close built-in function closes a channel, which must be either bidirectional or send only. It should be executed only by the sender, never the receiver, and has the effect of shutting down the channel after the last sent value is received. After the last value has been received from a closed channel C, any receive from the C will succeed without blocking, returning the zero value for the channel element, the form. Okay. Okay, it seems very so here it seems very easy. Here you close a channel, right? When you try to close the channel and try to receive value from it, so when I try to say just assign this one to a variable, okay, not here but here, okay, here I will say that foo, and I am trying to assign this to a variable right here. So this is S, but what about usage here? Why there is no OK then? If I say OK, okay, this usage is also okay. So when you try to receive a value from the channel, if it is a closed channel, then you will get a false here, right? False. But still, you can get value from the closed channels, right? When you enter the select statement, one of the cases should be executed successfully. Okay, you closed foo and bar, but when you try to select these cases, it can be, let's say that, asynchronously, right? So you don't know which one to happen. Since there are two foo in the cases, then the probability to receive a function from these foo cases is greater than the bar cases. So if I try to just duplicate, increase the value of this foo, most probably we will never see bar again, or this G. Yeah. It just jumps from first F and second F, but it is a bit hard to get G. Yeah, first G here. Okay, it is all about the probability, but I don't know. I don't think I will use this kind of notation inside one of my business use cases. The reflex standard package also provides try send and try receive functions to implement is plus default select blocks. I don't know it. Let's see. Oh. Okay. So it says that within the reflect package, there's a try. No. Reflect. But there is no try send. Go reflect try send. Okay. No. Symbols. I don't know, maybe it is all about Go version, but I am using the latest version anyway. Go. Yeah, the latest, but somehow I cannot see try and send. Okay. Data flow manipulations, data aggregation, data division, data composition. I think the receiving, okay, data. Okay, so the final chapter is about the data manipulation, but most probably we can handle it in the next section. So in 5 part, we can finalize the data flow manipulations, because I will need more time to consume these use cases. Okay, but okay. Thank you all, and have a nice day, have a nice evening, have a nice night. Thanks for watching. Bye.